All right. Hello. Camera. There we go. Let's go ahead and start it here. Couple things. Um, so because everyone's sort of still getting situated with what's going on with them and getting home and everything. Um, I have moved all the deadlines forward until April 10th. So if you look on WebAssign, there's nothing due before April 10th at this point. So hopefully this helps, um, helps anyone get sort of situated with what they need. Please don't, if you can, please don't wait until the last minute to do them, though. Otherwise, you might have a huge backlog all of a sudden. And I'm going to stagger the stuff from next week a little bit after that, just so not literally everything is due on the 10th. But figured this would be a good way to, especially for, our friends on the other side of the world here who have traveling home. They have, issues getting settled and other things going on. Anytime you do international travel, it's in a time like this, it's pretty tricky. So, but yeah, and then let's see what else. So that being said, all those deadlines are after the current date set for the next exam, which we're going to have to think a little bit about what that needs to be. Obviously, I don't want to make the exam before the deadline, at least this first set. And we're gonna have to figure out exactly what an exam means and how to do one at this time. So we'll get some figuring out done on that. Hopefully by the end of the week I can settle on something, but we'll see here. Sorry, I meant to make this go away. All right. Oh, I haven't changed that yet, have I? No, that's also supposed to go forward. I changed all the WebAssign stuff and I forgot we had a lab open still. I mean, again, submitting it, the earlier you can submit it, the better, just to get it out of the way. But thank you for reminding me. Okay, that is now also April 10th. Yeah. Okay, cool. Yeah, thanks for pointing that out. I forgot about that. All right, though. But yeah, we have an online faculty meeting going on tomorrow, and we'll see what kind of stuff's gonna go on there. Haven't done an online one of those, so this should be interesting. But maybe that'll give us some more hints about what's going on this semester. But anyway, for now, let's do what we can and learn some calculus. All right. So today's actually a fairly easy day. It's just, well, in comparison, anyway. So we just want to basically get our head around what an antiderivative is. And all this is think about, well, what function gives me this as a derivative? Right, so problem 1 here. we want to say, all right, find the most general antiderivative of 4x plus 7. So I'm going to swap some notations here, or use the integral notation here, I mean to say. So integral of 4x plus 7 dx. Right, because remember, the most general antiderivative is the indefinite integral. Right? So we want to think about, well, what function can give us an antiderivative of 4x plus 7? Well, remember, if we integrate the x part, so we can factor the constant out. When we integrate the x part, we get 1/2 x squared. And then for the 7, when we integrate a constant, we just get that constant times x, or whatever the variable here is. Right? And then add c. So normally we would, of course, simplify this a bit. Right? No big deal. And it's always a good idea, at least, when you're just starting to learn this and getting used to it, it's always a good idea to take this thing and differentiate it and make sure you get back to this part here. Right? So this is always a good way to check if you have the actual answer to your problem. Just differentiate your answer. So when we take the derivative, the 2 comes down, gives me a 4x. Derivative of 7x is 7. Derivative of c is just a constant, so the derivative is 0. And then this and this match, so we're good. Okay. So that's what I was saying. This is all there really is to it. Right, so let's look at the next problem. We are finding the antiderivative of 2x cubed minus 2/3 x squared plus 5x dx. Right? So we just want to think piece by piece, what the antiderivative would be. So we have 2 times 1/4 x to the 4th minus 2/3 times 1/3 x cubed, right? So we're just using that kind of power rule for antiderivatives here. Plus 5 times 1/2 x squared plus c. Right? And then, we'll simplify that. 1/2 x to the 4th minus 2/9 x cubed plus 5/2 x squared plus c. All right. And again, let's just double check this derivative here. All right. I won't write it out this time, but so 1/2 x to the 4th, the 4 comes down, I get 2x cubed, which is good. Right? 2/9 x cubed, the 3 comes down, so 2/9 times 3 is 2/3 x squared. Right? That's what I have here. 5/2 x squared, differentiate that, the 2 comes down. This becomes 5x, which is good. And the c is always going to go away when I do the derivative. So that should be it. All right. So let's do another one. So here we have the integral of x minus 5 squared dx. Right? So this one here, maybe in a couple days we'll come up with a better way to do integrals like this. But for now, the best thing to do is just multiply this out. Right? So I have integral of x squared minus 10x plus 25 dx. Right? And then when I integrate that, I get 1/3 x cubed. Here, maybe we'll skip this process and just go down to, this is going to be 5x squared plus 25x plus c. Right, so again, all we're doing here is just thinking backwards from taking a derivative. Right, just think like, whose derivative would be 10x? Okay, 5x squared. Whose derivative would be 25? That's 25x. Right. All right, let's look at the next one here. Problem 4, we want to integrate e squared dx. Right? So this is one of those, are you paying attention problems? Looking at this guy here, there's no way, or there's no variables in here. So this is just a constant. So the integral of this is just e squared times x plus c. Right? And again, that's just because, well, it's a number. It's a constant. Just as good as 2 or 5 or negative 10. Doesn't matter. Okay, so that's it. What is 5? Let me do 5 on the next page here. So 5, we're finding the antiderivative of the cube root of x squared minus x square root of x. All right, so now these have a little more interesting bit to them. This looks scary until you realize that it's just a bunch of powers of x, right? So when we take the cube root of something, we're taking the 1/3 power of it. So let me do this in a couple steps just to sort of make this clearer. So we're really doing this. And over here, this is x times x to the 1/2, right? Whenever we're doing antiderivatives, or even when we were doing derivatives, it's a lot easier to do these derivatives if you just think of them all as a power of x rather than, oh, here's the square root, or here's 1 over x, or anything like that. Right, so let's rewrite this one more time. This is supposed to be a 3, not a 2. So when I raise a power to another power, I multiply them. So this is x to the 2/3. Right? Over here, there's a secret 1 here, if you like. So when I multiply these two things, I add the exponents. So this is x to the 3/2. Right, so this is that, sometimes you just have to rewrite the function into a form that looks a bit better. And even when we learn some better techniques for integration, this is still a thing you're going to want to do, not infrequently. So now we just apply the power rule. This, right? So when we add 1 to this, it becomes to the 5/3. So we divide by 5/3, not 5/5. Right? And then here, when we raise this up, we add 1 to the exponent. This also becomes 5/2. And so we divide by that new power. Right? And then plus c. Right? So that's it. All right. Let's see, what's our next one here? Doing integral of 1/5 minus 2 over x dx. Okay. So here, we just think about what are the pieces of this integral. Well, 1/5 is just a constant, so this will be 1/5 x. Over here, we have 2 over x. So remember, the integral of 1 over x winds up being ln of absolute value of x. So here we're going to get 2 ln absolute value of x. Okay? Plus c. So in the lecture video, I go on about why it's absolute value x and not just x or minus x or something like that. Right? And again, here what we're writing down is the most general antiderivative. Right? If I wanted to specify, okay, x is positive, then I wouldn't need to bother with the absolute value. But here we're trying to do the most general answer possible, and so we do need that absolute value. All right. No, I keep missing my hand motions here. Let me maybe tilt that down a bit. Maybe that's better. We'll see. All right. So next one, problem 7. We are finding the antiderivative of 2 sine of theta minus secant squared of theta, d theta. All right. So, again, we're just going to attack this piece by piece. So the function whose derivative is sine is negative cosine. So when I integrate sine, I get minus cosine. So this will be minus 2 cosine theta. Right, that's for the first part here. Whose derivative is secant squared. That's tangent. Right, so this is going to be minus tangent squared theta plus c. Any questions at all so far? Give a second here. All right, cool. Because it shouldn't be. Thank you. Thanks for pointing that out. That definitely shouldn't have been squared. That's just regular tangent. Yep, that was a mistake. All right. Any other questions? Oh, all right. So let's look at the next one, number 8. We have integral of, let's see, what is 8? We have 1 plus 2 sine of x plus 3 over square root of x dx. Right. So this is another one where, we might want to think about rewriting it. We can rewrite the whole thing, or we can just rewrite the piece that needs to be rewritten. So this is fine, this is fine. This one, we want to think about this as 3x to the minus 1/2. That'll make our life a little easier. Right, so we integrate 1 and we get x. We integrate 2 sine x, we get negative 2 cosine x. That was completely unintentional that these two are the same. And integrate 3x to the minus 1/2. So this is 3x to the 1/2 over 1/2 plus c. Might look nice to simplify this a little bit. Right, so instead of dividing by 1/2, we'll just multiply that out front and we get this. Let's change the x to the 1/2 back to a square root even. Right? It looks a little bit nicer. You could stop at this top one. It's perfectly fine. There's not necessarily any reason to simplify that, but I think this looks a little bit nicer. Right? Okay, we got 2 more of these. 9. So here we're integrating. Oops. 2x to the 4th plus 4x cubed minus x over x cubed, right, dx. And we're thinking here about x greater than 0, right? So technically we do have to decide, generally speaking, whether or not to put x positive or negative, or, well, make this, on what interval do we want to do this integral? Now, there's ways to say, like in number 6 here, we can avoid that by putting on the absolute value. But in general, it's good to specify where your function sort of exists or doesn't exist. Right? But that's something you wouldn't have to come up with on your own, at least as far as the class is concerned. All right. So this problem, just like some of these other ones here, like number 5, for example, we really want to rewrite it into a form that we can actually use, right? So when we rewrite this, we're going to split this up and write each part separately and do the division. So maybe let's write out all the details of it here. So we're splitting this fraction up over the numerator. Right, and now we're going to simplify that. 2x plus 4 minus, now x over x cubed, right? That's 1 over x squared. So this is x to the negative 2. Right? It's good to keep that in mind. It'll make doing this a lot easier. Right? So now we just integrate. So integral of 2x is x squared. Integral of 4 is 4x. And when I integrate this, we can just go through the power rule for antiderivatives. So we add 1 to the exponent, and then we divide by that new exponent. And of course, we can simplify this and make it look nicer. Right? This actually looks like this, right? Because this -1 and this negative turn into a plus. And then we can take the x to the -1 and put it back down in the bottom. And then here's the sort of simplified form. Of course, if you want, you can leave this part as x to the -1. There's no harm in that at all. All right. Any questions? We're down to about the last one here of the first problem anyway. Right. So, was this number 10? So number 10, we want to integrate 2 to the t plus 2e to the t dt. All right. So now, this one is, again, just sort of a basic antiderivative. The second part is pretty easy. Right? The question is, well, what is the antiderivative of 2 to the t? Right? So to get that, we want to think back to, well, what is the derivative of 2 to the t? Right? So if we differentiate this, I know it's been a little bit since we talked about this, and we haven't done very many examples with it in there, but the derivative of this thing, remember, it looks just like an exponential function, but times ln of whatever the base is, right? So since the derivative multiplies by ln of 2, when I take the antiderivative, I need to divide by ln of 2, right? Because what I'm doing is I'm trying to get the output of the derivative to be just 2 to the t, so I need to take this part and put it in here. And so the derivative of 2 to the t over ln of 2 is going to be 2 to the t. So that means my antiderivative is 2 to the t over, make sure that looks like an exponent, over ln of 2. Right, and then that's it. That's the answer. Right? Yeah, so, integrating those exponential functions that aren't e to some power isn't really that bad. Just like the derivatives, you just have to remember to deal with ln of that base, right? So when you're differentiating, you multiply by ln. When you're integrating, you divide by ln. Right? Okay. Any questions there? Right. So before I go on to the next problem, let me just make the comment that there's a few basic functions whose integrals we can't do yet, really. Like integral of tangent, right? Integral of secant, integral of ln x. Right? There's a few of these that are pretty basic functions that we do want to know the integral of, but we can't quite do yet. But we'll eventually have a go at it. Actually, because it's my favorite function, I'm going to add integral of arctangent to this list as well. There's a bunch of these common basic functions that we'll work on over the coming days and weeks. Right? But we need some more techniques for that. Namely, U substitution and integration by parts. Right? Okay. Any questions about any of this first problem here? Awesome. Right. So the next set of problems, problem 2. Okay. So these are the sort of initial value problems that I was talking about in some of the lectures. So problem 1 here, we're looking at f prime of x is 1 plus 3 square root x, and f of 4 is 25. Right? So what we're kind of saying here is solve for f. Okay? So to solve for f, well, f of x is going to be the integral of this stuff. Right? X. So let's see here. We integrate this and we have x plus, let's see, this is 3 x to the 3 halves over 3 halves plus c. Right, so that's x plus 2x to the 3 halves. And then remember, we just need to use that initial value here. So f of 4, this is going to be 4 plus 2 times 4 to the 3 halves plus c. So that's 4 plus 2 times, now 4 to the 3 halves, so we're going to square root it and then raise it to the 3rd power. So square root of 4 is 2. 2 to the 3rd power is 8. Right, so this is 20 plus c. And this has to equal 25. So this means that c is 5. So f of x is going to be x plus 2x to the 3 halves plus 5. Right? That's our situation here. Okay. So look at part 2. So part 2 here, we're given the second derivative of f is minus 2 plus 12x minus 12x squared. We have f of 0 is 4, and f prime of 0 is 12. Right? So, well, we have sort of two options here for what to do. We can try and just integrate twice immediately and then use the initial values. I think it's better to sort of use them as they come up and just get rid of these arbitrary constants as quickly as possible. So we have to start with, all right, well, if this is f double prime, then f prime of x is going to be the antiderivative of this. And that is minus 2x plus 6x squared minus 4x cubed plus c. All right, so let's go ahead and get rid of this c. We know that f prime of 0, which is, well, really 0 plus 0 plus 0 plus c, has to be 12. Okay, 12 it is. All right, so we know that's 12. And so f prime of x is negative 2x plus 6x squared minus 4x cubed plus 12. Right? And then do it again. Well, f of x, right? If this is f prime, we should undo the derivative on that, and that should give us f. So integrate this. We have minus x squared plus 2x cubed minus x to the 4th plus 12x plus c. I'm just going to recycle that c. We can call it something else if you want, but we'll just recycle it here. Right? We know f of 0 is 4. So f of 0 is 0 plus, plug it in here, we get 0. Plug it in here, we get 0. Maybe I should use a minus there. Plug it in here, I get 0. And then c. And that has to equal 4. Right? And so c is 4. So f of x is, the order's a little weird here, but it's fine. So f of x is negative x squared plus 2x cubed minus x to the 4th plus 12x plus 4. Right. And there we go. All right. So any questions about either of these two problems here? Awesome. All right. So let's go ahead and go to actually the last problem for today, which is problem 3. Right? So here, the problem says that a car is traveling at 1,000 kilometers per hour when the driver sees an accident 80 meters ahead and slams on the brakes. Right? What constant deceleration is needed to stop the car in time to avoid a pileup, right? To avoid it from crashing into this big mess of cars ahead, right? So there's a couple pieces that are going to go into this, right? So this is going to be based off of, we're trying to basically say, if we have some position function, we know that its second derivative is going to be some constant acceleration a. Here we should expect a negative number for a since we're trying to decelerate, right? But if we start with this and use, say, we have an initial velocity, so s prime of 0 is v naught, and an initial position. Now here, we're not really given an initial position, but we may as well make the initial position where we're starting at. That's going to be 0. Right? And so the position function, by integrating just this constant twice, we're going to wind up with v naught t plus 1/2 at squared. Right? So it should be that basic kinematic equation we talked about in the lecture. Right? Normally there would be a plus s naught here, plus the initial position, but that's just 0. Right? Now in this problem, the car is traveling at 100 kilometers per hour. So we're going to make this 100. Right? Let me emphasize that this is kilometers per hour though. So S of t, this will be 100 t plus 1/2 at squared. Right? So how can we deal with this problem here? So this person is slamming on their brakes and they want to make sure that they stop before they hit the accident, right? So what velocity do you have to be at to be stopped? Well, you have to not be moving, which means you have to have velocity 0, right? So v of t equals 0 when stopped. So let's take the velocity function, which, remember, is the derivative of position. Right? So the velocity function is actually just going to be v0 plus at. So this is 100 plus at. Right? Okay. And we want to set this equal to 0. This is what we're going to need for the car to be stopped. All right. So what we're going to ask first is, well, how long does it take to stop? Right? In this case, we solve this for t, solve this equation here, solve this for t, and we get negative 100 over a. Now remember, a should be a negative number here, so this t will be positive. Now, how do we use that information? Well, we're going to take this number and plug it into S. Sorry, a little bit of writing here. 1/2 a negative 100 over a squared. Okay. Now the question is, this is when the velocity is 0. This time right here is when the velocity is 0. When do we need the velocity to be 0 by? Well, we need it to be 0 by the time... Oh, I didn't write the number down here. We need it to be 0 by the time this person would get to where the accident is. And the accident is 80 meters ahead. So we want S to equal 80 meters. Okay? So since this is measured in kilometers per hour here, we could switch this to meters per hour. That would be one way to do it. But then we're going to get 100,000 meters per hour. Maybe we don't want to say that. So 80 meters is equal to 0.08 kilometers. Right? Just divide this number by 1,000. Why did that do that? Right. So we're going to take that 0.08 and we're going to put that right here. Because right now our distance function is measuring in kilometers per hour. Or sorry, in kilometers. Okay. So we get to work this out, and now we can actually solve for a. So here we have negative 10,000 over a plus, when we multiply all this out, we're going to get 5,000 over a, okay, equals 0.08. And so this equation turns into negative 5,000 when we combine these two together over a equals 0.08. So a is going to be minus 5,000 over 0.08, which I can't do that off the top of my head. This is negative 62,500. Right? The units on this are kilometers per hour squared. Right? Now, if you want to change this to meters per second squared, the more typical the SI units, we would have to multiply by 1,000 to change kilometers to meters. And then hours squared, if we want to turn that into seconds squared, right? Each hour has 60 squared seconds in it, and we're doing hours squared, so we would square that, right? So this would be, let's see, this times 1,000 divided by 60 to the 4th. So this is approximately negative 4.823 meters per second squared, if you were interested in converting that. Right? So then we should actually answer this question here, which is that the car should decelerate at a rate of, it doesn't matter what units we use here, since it's, the answer we get is the 62,000 one. Let me just go ahead and write that. At a rate of 62,500 kilometers per hour squared. All right. So when you use units like kilometers and hours, you know, things tend to look pretty big. All right. So we still got 7 minutes here before class is officially over. Anyone have any questions they'd like to ask? All right. Let's see. Is there any interesting problem that maybe I could do one more of here? Let's see. There's not much going on yet, so yeah, maybe we'll stick with this for today here. So I'm going to record some more lectures today. Probably just like a bit after this, and then after office hours are done tonight. So those will be up tonight, the new material for Friday. And hopefully Monday as well. But just a little kind of concept of what we're going to do here is the next step for this stuff is to say, all right, well, here's, you know, some function, and I want to know sort of how much area is in here. Right? What's going on in there? How do I find that area? So that's what we're going to be talking about next. So I'm sure some, if not all of you, have done that already. But yeah, so look forward to that lecture. And with that, have a good afternoon, good evening. And yeah, let me know if you have any questions. Otherwise, I will see you Friday. Take care.